Speaker is a very special person for me. So when I was doing PhD, he was a master student of the same supervisor, and actually he was working on the same stuff, because for Professor Trautmann, he suddenly came up with some new ideas about optical geometries and CR structures in general relativity. So every pair of hands was needed for him, and for me it was fantastic time of collaboration, because me and Paweł spent all days, nights working together. Then when at night I was at home, I would give him a call at 3 o'clock and tell him that I have a new idea, and he would say, I've been just thinking about the same. So today's Paweł talk is on Twistor geometry of rolling bodies.
Thank you very much for a nice introduction. Yes, we collaborated with Jurek a lot. I calculated today, we wrote altogether 6 papers, so it is perhaps you are the person that has the most papers with me. That's correct, but we stopped this collaboration 25 years ago. Okay, and Jurek also said that one should always follow Ted Newman, so I can follow and say that my talk cannot be about loop quantum gravity, cannot be about quantum gravity, cannot be even about gravity. It cannot be about quantum field theory. It cannot be about quantum mechanics. So I will give you a talk about classical mechanics. Actually, it will be even worse. It will be a talk about kinematics in classical mechanics. So the motivation for this talk is a certain fact that was observed by Robert Bryant, but other people as well, around the year 2000. And this fact is from kinematics of classical mechanics. So if you just consider 2 balls, one of radius r, small r, and the other of capital R, and suppose that they are rolling on each other. So this mechanical system has obvious SO3 times SO3 symmetry, because this ball has SO3 symmetry, this has SO3 symmetry. So the symmetry of the system, the global symmetry, is immediately 6-dimensional in this SO3 times SO3. And even if you just add additional condition that this rolling is without slipping or twisting, there is still this global 6-dimensional symmetry SO3 times SO3. And what's happened at around year 2000, something happens when the ratio of these radii of these balls become from whatever ratio to ratio 3:1. When the ratio becomes 3:1, the local group of symmetry of such a kinematical system turns out to jump suddenly from dimension 6 to dimension 14. And what is even more surprising, the symmetry, local symmetry group of such system of rolling balls of relative radii ratio 3:1 has symmetry of exceptional split real form of the simple exceptional Lie group G2. So let me tell you a few words about simple Lie group G2. So it is the smallest of the 5 exceptional simple Lie groups. They were predicted to exist, these 5 exceptional simple Lie groups, they were predicted to exist by Wilhelm Killing in his classification of complex simple Lie groups obtained in 1887. And this smallest group has complex dimension 14. This complex simple exceptional Lie group G2 has actually only 2 real forms. The first one is compact real form, and the other is non-compact. The non-compact one can be characterized by this, that its Killing form is not definite. Okay, so it was predicted by, so Killing had this group predicted, but he didn't have realization of this, but he predicted that it should be realized as a transformation group on some 5-dimensional manifold. So there should be a structure on a 5 manifold that has this split real form of Lie group G2 as a symmetry. So this prediction of killing, so he predicted it in his classification in 1887, and this prediction turns out to be true. A few years later, Elie Cartan and Friedrich Engel realized this group as a symmetry group, transformation group of some geometric structure in 5 manifold. So this realization, I will just quickly tell you how you can realize this group. So consider R5 and somehow open set around the origin of R5, put coordinates x, y, p, q, z, and now consider 2 vector fields, x1 and x2, which in these coordinates looks like this. So you have a open set in R5, which is your 5 manifold, and on this 5 manifold you have these 2 vector fields, and these 2 vector fields define rank 2 distribution on this 5-dimensional manifold. So I call this distribution, which is spanned by these vector fields x1, x2, Cartan-Engel distribution. So what can I do with such a distribution? If I have a distribution, one can search for local diffeomorphisms of this open set that transforms distribution to itself. So if such local diffeomorphisms exist, they form a Lie group, and this Lie group will be called group of local symmetries of the distribution. Perhaps finding this diffeomorphism is a bit complicated, so one can try to find infinitesimal versions of them, so like killing equations. So one can consider vector fields on this U that preserve the distribution, and these are just linear inhomogeneous equations for this vector field X, and you can solve them. And when you solve it, you will get these vector fields define a Lie algebra, and you can just look for the Lie algebra of symmetries of this rank 2 distribution. So you can ask what is this Lie algebra, and the answer is given by Cartan and Engel that the Lie algebra of symmetries of this particular distribution is 14-dimensional. It is actually isomorphic to the split real form of this exceptional Lie algebra G2. So this was what you have as a result of Cartan and Engel from 1893, and it was the first ever realization of this Lie group G2. So it was not the compact group G2 that was first understood and realized, but the non-compact one. Okay, and it is realized as this symmetry of this Cartan-Engel distribution. Okay, so let me make a bit of characterization of this Cartan-Engel distribution. So I need few notions from the theory of distributions, very simple ones. So if you have any distribution D on a manifold, then you can consider a sequence of distributions. So you take your distribution D, call it D minus 1, and now consider a commutator of D minus 1 with D minus 1. So, and then define it as D minus 2. Then take commutator of D minus 1 with D minus 2. Define it as D minus 3. D minus 1 with D minus 3. And in this way, you will just get a sequence of distributions. And you can look at rank of this distribution, of this sequence of distributions at every point. And this rank is called growth vector of a distribution D. So of course, if the distribution is integrable, then already D minus 1 is just the last one, because commuting D minus 1 with D minus 1, you still are in D minus 1. But if it is non-integrable, then you have this sequence. And then you have this growing vector, which is just called growth vector in terms of these ranks of these consecutive distributions. Okay, so this growth vector is the simplest local diffeomorphic invariant of a distribution. That's a general fact. And among all distributions, there are some distributions that have this growth vector to be constant over entire manifold. Okay? And sometimes there are such distributions that after several steps, after a finite number of steps of just like taking these commutators, you produce the entire tangent space. So if such, it turns out that Cartan-Engel distribution is precisely like this, that it has constant growth vector, it starts with rank 2 of your rank 2 distribution, which is Cartan angle. Then d minus 2 has rank 3, and d minus 3 already has rank 5, and it's therefore already second commutator gives entire tangent space. So in this sense, the Cartan angle distribution is a 2-3-5 distribution. Okay? So this is how they call it. This is an example of 2-3-5 distributions. So now I said that this is an example of 2-3-5 distributions, which means that I'm just trying to tell you that there are non-equivalent 2-3-5 distributions. And it's really like this, but to tell you what does it mean, I have to define the notion of equivalence. So if you have two distributions, they are locally equivalent if there exists local diffeomorphism transforming distribution to distribution. Okay, so, and it turns out that in general, if you give me two 2-3-5 distributions, they are not equivalent even locally. For example, if I just change my vector field, you remember that I had these two vector fields defining this Cartan angle distribution. There was some vector x1 and x2. x2 is here the same, and now I change the coefficient here, which was 1/2 q squared in the Cartan angle, to an arbitrary smooth function of variable q. So if I take something like this, it turns out that if I now consider span of vector x1 and x2, and I define this rank 2 distribution on the same u, then it turns out that it's always 2-3-5, provided that the second derivative of this function f is non-zero, like, for example, it was for 1/2 q squared when this derivative was equal to 1. But if it turns out that various f's define 2-3-5 distributions which are not usually locally equivalent to the Cartan angle one, and actually it turns out that for a function f to define a 2-3-5 distribution to be locally equivalent to this Cartan angle one, this function should satisfy some horrible ODE. Why I'm telling this horrible? Because it's something like nonlinear, highly nonlinear, and it's of high order. It is of 6th order derivative. So somehow for this guy to be locally equivalent to this Cartan angle, this function f should satisfy this ordinary differential, nonlinear ordinary differential equation of order 6. I say that this equation is horrible, but it is not that bad, because if you just count the homogeneity in derivative of each term, homogeneity of this term is 12. It is 6, 3 times 2, 6 plus 6 is 12. Each term has homogeneity 12 of the derivative, so it means that this thing admits solutions in terms of monomials, like q to the power n, and there will be some constraint on this n. So there are various n's possible here that this f gives a distribution that is equivalent to Cartan angle. Okay, so that's what you can ask how on earth I get such a crazy equation. First of all, it's not me but Elie Cartan, and but to comment about this, let me tell first that it follows that this Cartan angle distribution is the most symmetric among all 2-3-5 distributions. So if you give me a 2-3-5 distribution, only the Cartan angle one has locally 14-dimensional group of symmetries, which is just equivalent to simple Lie group G2. If you just perturb this f in such a way that if you just give me one that is non-equivalent, if it has symmetries, either it has 14 symmetries or there is a gap between symmetries, and it jumps from 14. The next possible locally non-equivalent one, which is symmetric, may have symmetry 7. So the symmetry drops from 14 to 7 suddenly. So these are such beasts. So it's in 1910, Elie Cartan gave the full set of local differential invariants, which can be used to determine if 2-3-5 distributions are locally equivalent. In particular, Cartan associated a certain G2-valued Cartan connection to any 2-3-5 distribution, and it is the curvature of this Cartan connection that tells if two distributions are equivalent or not. Okay, so for example, the distribution for a 2-3-5 distribution to be locally equivalent to this maximally symmetric one, to this Cartan angle one, a certain part of this curvature, which is called harmonic curvature, must identically vanish. Okay, so it turns out that this harmonic curvature, whose vanishing is equivalent for the distribution to be equivalent to this Cartan angle one, is actually a certain quartic. So for people in general relativity, it immediately comes to their mind like self-dual Weyl tensor, but it is not self-dual Weyl tensor, although algebraically it is a tensor like this. So the difference between Weyl tensor, when you consider Weyl tensor of a conformal geometry in dimension 4, this Weyl tensor, which is harmonic curvature of this parabolic geometry, is only of the second order in terms of the defining functions of the conformal geometry. Here, this lowest order invariant is of 6th order. So there is a certain quartic who must vanish for this 2-3-5 distribution to be equivalent to Cartan angle one, and this quartic is just like a GL2R 4th rank symmetric tensor, GL2R invariant for symmetric tensor. Okay, so it is a result of Edouard Goursat from, I believe, 1921, that every 2-5 distribution can be locally written in this coordinate system as I wrote before, x, y, p, q, z, with a certain function f, which now can so if you give me any 2-3-5 distribution, it locally admits these coordinates, and it is defined in terms of this one function of 5 variables, and this is 2-3-5 if and only if the second derivative with respect of q of this thing. So if you just take this f to be, as in my case, two transparencies before, that f only depends on q, then it turns out that this Cartan quartic is in our language of type n, and this is the 6th order equation that this must vanish for this thing to be locally equivalent to this one with G2 symmetry. In general case, all these psi's or phi's are non-zero, and for a Cartan angle, this general Cartan angle distribution, this function f must satisfy these 5 nasty PDEs for this distribution to be locally equivalent to Cartan angle and have to G2 symmetry. So let me just summarize this. My talk has 3 parts. The first part is just story about 2-3-5 distributions. So that's the part, and as a summary of this is that among all 2-3-5 distributions in dimension 5, there is a subclass given up to local diffeomorphisms whose Lie algebra of infinitesimal symmetries is isomorphic to the split real form of the simple exceptional Lie algebra G2. Given a 2-3-5 distribution on a 5 manifold, one determines if it is locally diffeomorphically equivalent to the one with G2 symmetry by looking at the Cartan's quartic, and it has G2 symmetry if and only if the Cartan quartic vanishes. So that's the end of part 1 of my talk, and part 2 of my talk is about this, where I can find in practice these 2-3-5 distributions, when I can find such objects, when I can find it in nature. Do they exist in nature? I don't know if they do exist in nature, but I be talking now about something which is closer to this community, namely about totally null planes in 4-dimensional geometry with a metric. So let me start this part of the talk with a stupid question. What is the fundamental difference between R4 with Riemannian metric and R4 with Lorentzian metric? And of course, his well-known answer is, well, in Lorentzian case, we have real null vectors. So for example, this vector is null in this metric. So if I just ask what is the difference between Lorentzian case and split signature case, then the answer is, but now I have something new. I have real totally null planes. So in split signature, I have real totally null planes. For example, this vector and this vector, both of them are null in this metric. They are orthogonal to each other with respect to this metric. Therefore, they define a plane which is totally null, meaning that the metric, when restricted to this plane, is 0. So from this slide, what I want you to remember is that in split signature case in 4 dimensions, one has real totally null planes. So, for example, if I have a given totalinal plane, as I just defined on the previous slide, spanned by vector n1 and n2, now I can take my structure group of this geometry, which is just SO22, and actually I will take the identity component of this SO22, and I will be acting on this plane by SO22 group. So since SO22 preserves nullity, I will get another, taking an element of SO22, I will get another totalinal plane. And actually I will have entire orbit of the action of this SO022 onto this plane. And it turns out that this orbit is actually a circle. There is an entire circle of these totalinal planes which are on the same orbit. Okay? And here is this explicit parametrization of these circles. This is null, this is null, this is orthogonal to each other, and actually this just continuous deformation of this one. So this is the orbit of this plane that I started. So if you have totalinal planes in dimension 4, they define a line of a bivector. And it turns out that if you start with a totalinal plane, a line of its bivector is either self-dual or anti-self-dual. So we say that a totalinal plane is self-dual or anti-self-dual depending on what is the self-duality of this bivector. And it turns out that, for example, this entire orbit that I just described transparency before is an orbit of totalinal planes which are self-dual. So if I start with another one, so before I had 1, 0, 1, 0 here, and I had 0, 1, 0 plus 1, and now I take minus 1, it turns out that this plane is still totalinal, but it's just anti-self-dual, and now again, acting by the group, I will get entire orbit of this totalinal plane, and it follows that the space of all real totalinal planes in the split signature, the space is just consisting of these two orbits. Either they are just those that sit in this S1 of totalinal planes self-dual, or S1 of totalinal planes anti-self-dual. So that's what I have. And now, everything what I said so far was in a vector space equipped with a split signature metric of signature 2, 2. Now I want to do the same over a manifold. So now I start with a 4 manifold with a split signature metric, and I assume that it's oriented. Then I know what is self-duality and anti-self-duality. And now at every point, I have a tangent space, and in this tangent space, I have this circle of totalinal planes, real totalinal planes, which are self-dual. So this defines a bundle of circle bundle over the 4 manifolds. So I have my 4 manifold with split signature metric, and at every point I have a circle attached of these totalinal planes which are self-dual. I call this a circle Twistor bundle of a split signature 4 manifold. And note that the existence of this small bundle is a special feature of signature 2-2. In signature plus plus or Lorentzian case, there will be a sphere bundle. Here I have circle bundle over this thing, because I'm only considering real totalinal planes. Okay, so I have this, and now this bundle, this circle bundle over this split manifold, has a lot of geometric structure. So in particular, of course, there is a vertical space, but because I started with a manifold, so these are circle bundle over natural circle bundle over this pseudo-Riemannian manifold. So then this pseudo-Riemannian manifold has Levi-Civita connection, and this Levi-Civita connection defines also a horizontal space in this Twistor bundle, and therefore I have a split of the. At every point, I have a split of the tangent space to this circle Twistor bundle onto vertical part and the horizontal part. So now what I have more here is that now a point in the bundle, so here is my 4 manifold, and here is a point over a point on my manifold. So a point in the Twistor space over my manifold. So what is this point? This point is a real totalinal plane, self-dual null plane here. But there at this point, I have a horizontal space. So I can take this two-plane corresponding to this point and lift it horizontally to its point. In this way, at every point of this twistor bundle, I will have a two-plane. So I will have a 5-dimensional manifold with a two-plane associated to every point of this. Okay? So I call this, so this defines a rank 2 distribution on this twistor manifold. There is much more of this structure here, but I really will be only concentrating on this rank 2 distribution. So this is called twistor distribution. And note that what I got suddenly out of nothing, I started with a split signature 4-dimensional manifold, and out of nothing I created a 5-dimensional manifold with rank 2 distribution. So if I have a rank 2 distribution, I'm close to the first part of my talk when I was talking about 2, 3, 5 distribution. So the natural question, there are a lot of natural questions appearing here. So the first thing is what shall I assume about my structure downstairs that this distribution is integrable? But what shall I assume that is 2, 3, 5? Because that's what I want. And suppose that I assume something about the metric that is 2, 3, 5. What I have further to assume about the metric, that it has G2 symmetry, that this distribution, or that is just locally equivalent to Cartan angle. And there are a lot of questions. So I have questions like this. And the answer to the first question is essentially due to Roger Penrose years ago. So here is the theorem. So this twistor distribution is integrable if and only if the split signature metric on M has anti-self-dual Weyl tensor. So it means that the self-dual part of the Weyl tensor of the metric must vanish. If it vanishes, then this rank 2 distribution, this twistor distribution, is integrable. But I'm not interested in integrable distributions. I am interested in 2, 3, 5 distributions. So I'm asking when it can be 2, 3, 5 distribution. And there is a surprise, because this distribution, depending on the conformal properties downstairs, could be 2, 3. It could be 2, 3, 4. It could be 2, 3, 4, 5. It could be 2, 3, 5. So there could be a lot of conditions that this distribution could be, depending on conformal properties of the metric. But it turns out that actually there is dichotomy. Either this distribution is integrable, or almost everywhere on the twistor bundle it is 2, 3, 5. Almost everywhere. Provided, and this will be 2, 3, 5, if only there is some component of the self-dual Weyl tensor that is non-zero. So let us assume that the self-dual part of the Weyl tensor is non-vanishing over an open set. And then the quick question that I would like to ask, which metrics have their twistor distributions locally equivalent to the Cartan angle one? So I would like to understand, so somehow if I assume that the Weyl tensor is not anti-self-dual, then I somehow embedded a conformal split signature 4-dimensional geometry in 2, 3, 5 in the geometry of 2, 3, 5 distributions. So somehow I would like to now understand what shall I assume about my curvature of my 4 manifold to have a 2 distribution to be G2 flat, right? So I wrote that is a difficult question. Okay, depends what does it mean difficulty. You just make the construction, and you are supposed to calculate the Cartan quartic depending on your metric. And this Cartan quartic is simply horrible. It is that horrible that in general case I cannot calculate it. I tried, but I cannot. So it means that it's calculationally difficult. I cannot even write the equations. So if I cannot write equations, I ask my friend Daniel Ahn if he can help me with computers. But Daniel said, "Oh, why don't you make something simpler? Why don't you take 2 surfaces? Why don't you make some simpler assumption about something simpler? That consider a 4 manifold which is just a Cartesian product of 2 Riemannian surfaces." So it turns out that in this case we can calculate something. So if I consider now a surface with a Riemannian metric, and such that its Gaussian curvature is kappa, and I assume that this surface has a killing vector. And now I take another surface, and I assume that this other surface has constant Gaussian curvature. Then I can consider a four-manifold, which is Cartesian product of them, with a split signature metric being the difference between G1 and G2. And then I can try to calculate this Cartan quartic for the Twistor distribution associated with this metric. And even in this case, I cannot calculate it. But I can calculate some components, and I try to do something with these components. And I manipulate with the components. I discover that there is a constraint, that there is a necessary algebraic constraint for this Twistor distribution to have G2 symmetry. And it's a very interesting constraint. It is a constraint like 9 kappa minus lambda, or kappa minus 9 lambda times lambda must be 0. So you say that it's asymmetric because my assumption was asymmetric, but it's simply like this. So obviously, this can be satisfied only in two situations. Either the ratio of the curvatures of these surfaces is 1 to 9 or 9 to 1, or the constant curvature one must be flat. Okay, so that's what you get here. And then if you now specify, so this is a very nice condition, because now you can specify for that now both of these guys have constant curvature, and then you have this one of these, and then it turns out that for the first situation, when the ratio of curvatures is 1 to 9 or 9 to 1, the Cartan quartic actually vanishes. So it is even on leave. So it turns out that the case when the ratio of constant curvature is equal corresponds to Twistor distributions with G2 symmetry. So at least I find something. Okay. I was not very satisfied with this, not happy. I even, when I remember when Daniel An came to me and gave me this result, I said, okay, so what? Nothing. Okay, so now, so that's a corollary. So I should now comment about the remaining case when lambda is equal 0. But before of this, I pass to the third part of my story, which is just rolling of two surfaces on each other. So I want to describe the space of possible positions for two smooth rigid bodies that roll on each other in the free space. So I idealize these bodies as such that I consider their boundaries, which I assume that there will be just like these Riemann surfaces with Romanian metric, which is just coming from R3. And now I would like to know what is the position space, what is the configuration space of this rolling system. So I have to count the dimensions. So it's quite easy, because how many numbers I need? I need a point on one surface, on the other, which will be just the kissing point. So there are two numbers here, two numbers here. And I need still identification between the tangent spaces. So I need a rotation that transforms one tangent space to the other. So I need 5 numbers. I need a point on one surface, point on the other surface, and rotation identifying tangent spaces at each point. So this is clearly a 5-manifold, and this 5-manifold is actually a circle bundle over a Cartesian product of my surfaces defining my bodies. So I was talking about some circle bundle over 4-dimensional manifold with a Cartesian product of surfaces, and now I have something like this. So it turns out this God would be cruel if these two spaces were not the same. And actually, there is a simple bundle isomorphism between configuration space of these rolling surfaces and this Twistor bundle, circle Twistor bundle over this split signature manifold, which is Cartesian product of the boundaries of these surfaces. So one has to think how to create this isomorphism. So I have on one side, in the configuration space, I have point on one surface, point on the other, and the rotation. And on the other space, the point is just a totalinal plane. So how can I associate the totalinal plane to this point, and rotation? So rotation is between this space and this space. So these are just, so this space is two-dimensional, this is two-dimensional. So we have four-dimensional vector space, which is just a direct sum of this space and this space. And I have map from here to here. So given a map like this, I consider a graph of this map in here, right? So what you now get, you just given a rotation, you consider a graph of this map in this R4, and this graph is a linear space which is actually a two-plane, and this two-plane is totally null with respect to the metric G1 here and minus G2 here. So this identifies the bundles T sigma 1, sigma 2, and the Twistor bundle over this split signature manifold. Okay? So in a way, from this, I know that I can somehow identify configuration space of these rolling surfaces to the Twistor bundle, circle Twistor bundle of these totally null planes associated with the surface sigma 1, sigma 2, and the manifold sigma 1 cross sigma 2 with this metric. So now if I think about my rolling surfaces, they draw a curve in the configuration space, or this curve is just a curve in the circle Twistor bundle. So there is a particular kind of rolling where this curve is always tangent to the Twistor distribution. So now the question is, what this particular rolling means. So if these surfaces roll, they draw a curve in the Twistor distribution, but what if they roll in such a way that this curve is all the time tangent to the Twistor distribution? Then, so let's count. The tangency condition means that I have a linear constraint on velocity at each point. And actually, since this velocity should be in two-plane at every point, so there are three linear constraints. So do I know physical movement that will give me three linear constraints on velocities of the system? So maybe I do. So I will be calling rolling without slipping or twisting. So I want that these surfaces will be now rolling without slipping or twisting. What does it mean that they roll without slipping? Well, at the point of kissing, the velocities must be the same. The linear velocity must be the same. These give two linear constraints. And moreover, they should no twist, namely not doing this, which is one more constraint. So these are just three constraints. I found a three linear constraints, and God would be cruel if it is not this constraint that gives the Twistor distribution. So it's really like this. And the theorem we have here, the curve corresponds to rolling without slipping or twisting of these two surfaces if and only if, when viewed in the circle Twistor bundle, it is always tangent to the Twistor distribution D. Okay? Okay, so that's, I still have 2 minutes. Let me. So in particular, now I can interpret this condition of Bryant, that Bryant had these two spheres of ratio 1 to 3 that when rolling were giving a G2 symmetry. And it's obvious why now, because I had this result about 1 to 3. So now the question is if I have other pairs of such rigid bodies having this property. And it's rather surprising. It would be surprising that I have, and it's almost impossible. People don't believe that there is any other pair of surfaces that have this property, that have symmetry G2 when rolling without slipping or twisting. Of course, I didn't know about this, and I wrote the equations, and I was just like, and in particular, I get this algebraic constraint, and I told you that there is this open situation that there are these two surfaces, one with Killing vector, one with constant curvature, and if this constant curvature, it was necessary condition for vanishing of Cartan quartic. So I didn't say anything about this. So it turns out that in this case, I can calculate this Cartan quartic to the very end, and actually I can solve totally the problem if there is another surface with Killing symmetry that makes this Cartan quartic 0. And actually there are 3 different surfaces that when rolling on a plane have the G2 symmetry. Yeah, so that's what they are. How do they look? They look boring. I don't know what to do with them. I asked my friend Ian Anderson what to do with these surfaces that rolling on a plane have G2 symmetry. He told me, slice them and just call some tire company, because they roll without slipping or twisting with highest symmetry, and they should be very good for them. So that's what they are. So when we just get these surfaces, it was sort of like surprise, especially for Robert Bryant. So a few years later, so we found some other surfaces than these two balls of ratio radii 3:1 that have G2 symmetry. And the question was, we found them by some ansatz. The question is, are they all? So then Robert wanted to solve this situation. And a few years later, he wrote me a letter saying that it reminded me of the leftover question of determining whether there are any other examples besides the constant curvature ones and your rotational symmetric examples rolling over the plane, having this G2 symmetry. So I took another look at the calculations and at the formula that I worked out for Cartan's C-tensor, this Cartan quartic in this sense. And then he said it took a little thinking, but based on this, I now have a proof that if a pair of Riemannian surfaces has the G2 rolling distribution, then at least one of the two surfaces has the constant curvature. So our assumption that one has constant curvature was not so stupid. Actually, it follows. But Robert still is unable to prove that the other should have killing symmetry. If he proven this, that would be the all. But if not, it is an open problem. Thank you very much.